Welcome to the Deep Dive. We're the show that, well, we skip the surface level stuff, right? We go straight into the details, the core ideas, trying to turn really complex information into something you can actually grasp, something crystal clear.
That's the goal.
And today, we are diving headfirst into something pretty huge. It's one of those grand quests in physics, the search for a theory of everything, something that ties it all together.
It's the holy grail, really. Been driving physics for centuries.
Exactly. And we have the standard model of particle physics, which is, it's incredible, right? An amazing achievement.
Oh, absolutely. It describes 3 of the 4 fundamental forces with stunning accuracy. Quantum level stuff. It's predicted particles, nailed their interactions. It's the bedrock of modern particle physics.
It really is a triumph. But, and there's always a but, isn't there?
Always. It's brilliant, but it's not the full story. It tells us how things work incredibly well, but it often just stops short of telling us why.
Leaving these massive questions hanging.
Huge questions like, why do particles have the masses they do? You look at an electron, then a muon, 200 times heavier. A photon, massless. Why? The standard model doesn't really give a fundamental reason for those specific values.
And the forces themselves. Electromagnetism, weak, strong. Their strengths are wildly different.
Wildly, like orders and orders of magnitude different. The strong force inside a proton is unbelievably strong over tiny distances. Then electromagnetism reaches across galaxies, but is, comparatively weaker locally. Why such a massive range?
These aren't just little details. They're fundamental.
Exactly. Core questions. And, people have tried with unified theories, quantum gravity models, but they haven't quite cracked it, often getting really complex or speculative without solid experimental footing. It's left our understanding a bit fragmented.
Right. Those deep, nagging questions that physicists probably lose sleep over.
Yes.
The missing pieces. And that, listeners, is exactly why today's deep dive is, well, I think it's going to be really fascinating. We're going to unpack a really revolutionary paper. It's by Philip Randolph Lillian, titled Coherence, Coefficient, and Coherence Amplitude.
And this isn't just tweaking the existing models. This is proposing something fundamentally new.
Yeah. It introduces the unified coherence theory of everything, or UCTE.
UCTE offers a completely different viewpoint. It's pretty radical. It says, look, everything we see, tiny particles, huge stretches of space-time, they aren't fundamental things in themselves.
Okay, so what are they then?
They emerge. They arise from one single foundational principle, coherence.
Coherence, like things being in sync, or is it more technical than that?
It's a bit more technical, but that's the intuitive idea. Think of coherence as the master key. UCTE suggests that things like mass, charge, force strength, they aren't just random properties assigned to particles. They're actually reflections, or maybe residues, of how this underlying coherence operates, specifically the geometry of how it reduces or changes.
Okay, hold on. So the universe isn't like Lego bricks that just exist.
Right.
It's more like ripples or patterns in some kind of fundamental coherence field. Is that getting closer?
That's a really good way to think about it. Exactly. Everything is a specific manifestation, a pattern within this single underlying field.
Okay, so our mission today, let's break this down. It sounds complex, but you're saying it's also elegant.
Incredibly elegant once you grasp the core ideas.
So we'll define the key terms, look at the core equations, don't worry, we'll make it make sense, and try to visualize how it pulls together all these different bits of physics, forces, mass, everything.
Yeah, hopefully giving you some of those aha moments.
Right. The goal is to shortcut you to being genuinely well-informed on this, because it really could be a game changer. You should walk away with a much richer picture of how reality might be put together.
And what that might mean down the line.
Okay, so let's start right at the foundation. You mentioned the standard model treats forces, particles as fundamental. We know how they work incredibly well.
Yeah, the precision is amazing.
But not why they are the way they are. Why these specific forces? Why these masses? It's like having incredibly detailed blueprints for individual components of a machine.
But no schematic for the whole machine itself.
Exactly. No picture on the box. We've been inferring the big picture just by looking at the pieces.
Precisely. We have the math for the dance, but not the reason for the dancers or the music. And like we said, grand unified theories, quantum gravity, they've tried to bridge these gaps, but haven't quite given us that satisfying, simple answer. They often end up adding more complexity, more dimensions, things we can't easily test.
Right. So this is the context where UCTE steps in, proposing a different approach, A radical simplification, you said.
Yes, it goes right to the root. The core idea, the central postulate of UCTE, is coherence as the generative principle.
Generative principle, meaning it creates everything.
In a sense, yes. It posits that all physical structure, literally everything, forces, particles, maybe even space-time, doesn't just exist independently. It arises from coherence. They're seen as emergent phenomena. Think about a vortex in a river.
Yeah.
The vortex is real, you can see it, it has properties, but it's not a fundamental thing, right? It's a pattern that emerges from the flow of the water.
Right, it's the water doing something.
Exactly. UCTE says something similar about reality. Everything we observe emerges from quantized reductions in coherence with the omnilectic vacuum.
Okay, quantized reductions in coherence, that sounds important. And omnilectic vacuum, what's that? Sounds very sci-fi.
It does sound a bit grand, doesn't it? But the concept is key. It's not empty space in the way we usually think of it. It's a state of hypercoherence.
Hypercoherence.
Imagine a perfectly still, infinitely large ocean, utterly calm, perfect symmetry everywhere. That's the omnilectic vacuum. It's not empty. It's pure potential, perfect, unbroken symmetry.
Wow, okay.
And every single thing in our universe, every particle, every force field is basically a disturbance in that ocean. A ripple, a localized spot where that perfect symmetry, that perfect coherence has been reduced or lost.
So reality is deviation from perfection.
In the UCTE view, yes. All observable structure comes from deviations, reductions from this underlying hypercoherent state. It's the ultimate baseline.
Okay. If coherence is the baseline, how do we measure these deviations? How do we quantify it? You mentioned two key things.
Yes. UCTE introduces two essential metrics to quantify these coherence dynamics. They are the coherence coefficient, which uses the symbol lambda c,
Lambda.
and the coherence amplitude, symbol AC.
Okay, lambda c and amplitude. Well, let's break those down. What does the coherence coefficient lambda c tell us?
So lambda c is a dimensionless number, meaning it doesn't have units like meters or kilograms. It just ranges from 0 to 1.
Out of 1. Yeah.
And it directly measures the degree of alignment or symmetry that a system, like a force field or a particle, has with that hypercoherent vacuum state.
So it's like a purity score. How close to perfect stillness it is.
Exactly. Think of it as purity or order. A high lambda, close to 1, means it's very close to that perfect vacuum symmetry. Very ordered, very pure, like the electromagnetic field, as we'll see.
And a low lambda, near $.
That means strong decoherence. Significant deviation, fragmentation, loss of that initial symmetry. Think of the strong nuclear force. So lambda c captures the informational aspect, how much order is left.
Okay, informational aspect, order, purity. That makes sense for lambda cap. What about the other one? Coherence amplitude. ACC Sage, what does that measure?
ACCOs is the flip side. It represents the projected field strength, or you could say the resonance magnitude that arises because of that coherence reduction.
So when the coherence drops, something else appears.
Precisely. When that perfect symmetry gets disturbed, it doesn't just vanish into nothing. It manifests as an energetic projection and intensity. AC measures how strong that projection is.
So it's the energy or the force that results from losing coherence.
Yes, the intensity of effect. A higher ACM means more energetic condensation, a stronger field compression. And interestingly, this can happen even if the coherence coefficient lambda cax is low. So ACL is the energetic aspect, how intensely the lost coherence expresses itself.
Right. And this leads to what you call the core insight, the perhaps counterintuitive part, the relationship between lambda regard and ace theta.
Exactly. This is maybe the most crucial finding in the paper. It's the inverse relationship between them.
Inverse. So as one goes up, the other goes down.
Generally speaking, yes. As the coherence coefficient lambda order decreases, the coherence amplitude AC, the energetic expression or field strength, tends to increase.
But that feels backwards. If something loses order, becomes less coherent, shouldn't it just weaken, fade away?
That's the intuition from some systems, but UCTE proposes this inverse relationship is fundamental to how forces arise. Think of it like squeezing something diffuse.
Okay.
If you have energy spread out very evenly and coherently, it's stable, maybe low intensity locally. But if you break that coherence, squeeze it, condense it, the energy becomes much more intense in that localized spot.
Ah, I see. So losing the overall coherence, the spread outness, allows it to concentrate its punch locally.
That's the idea. Less coherent means more deviation from the vacuum, and that deviation manifests as a stronger, more condensed local effect or force. It's like trading coherence for amplitude. This paradox is exactly what UCTE uses to explain why forces have different strengths and ranges.
Okay, that clicks. Trading coherence for local intensity. That sets the stage perfectly for talking about the forces themselves.
Right. So let's take this inverse relationship, lambda c down, AC up, and apply it. How does UCTE actually use lambdas and AC to describe the fundamental forces we know, like electromagnetism, the weak force, the strong force?
This is where the theory gets really predictive and connects to actual measurements. It provides a really elegant framework. Let's start with electromagnetism. In the standard model, that's the U1 gauge group.
Right, light, electricity, magnetism, all that.
In UCTE, electromagnetism is seen as representing near total coherence. It's the force that's closest, the least deviated from that perfect hypercoherent vacuum.
So it should have a high lambda SF.
Exactly. Its lambda c is estimated to be around 0.915,
Yeah.
very close to 1. Okay. And following the inverse rule, its ACE, its amplitude, should be low.
Yes. And the resulting ACE is about 0.085. Now, here's a really striking point. This value, 0.085, is numerically almost exactly the square root of the fine structure constant.
Whoa, wait. The fine structure constant, that's like the number for electromagnetism, roughly 1137.
That's the one. AC approx 0.085 approx 1 SOLCOR to 1 R. That's a major numerical alignment that pops right out of the UCTE framework.
That's pretty compelling.
Right.
So the interpretation is it's weak locally because it's so coherent.
Precisely. It's not highly compressed or decohered. That high coherence allows it to spread out, have that extended influence across vast distances, binding atoms, carrying light across the cosmos. Weak amplitude, long reach.
Okay, makes sense. What about the next force down the coherence ladder? The weak interaction, SU2 group, right? Responsible for radioactive decay.
That's it. UCTE frames the weak force as involving moderate decoherence, a step down from electromagnetism. Its lambdas is estimated around 0.875.
Still pretty high, but lower than 0.915.
Right. And this leads to an ACR off of about 0.125. And again, there's a numerical connection here. This amplitude, when you normalize it correctly, matches up with the Fermi coupling constant, which is the key strength parameter for the weak force.
Another numerical hit.
Another one. Now, even though its lambda un is relatively high, the weak force is known for being very short-ranged, acting only inside the nucleus. UCTE explains this through its specific decoherence pattern and the broken symmetry involved in its interactions. It's localized because it's more decohered than EM, causing transformations like particle decay.
Okay, and then the big one, the strong force, SU3, the powerhouse binding quarks and protons and neutrons.
Right. For the strong force, UCTE says this represents extreme coherence reductions. Like the coherence has almost collapsed compared to the vacuum state.
So much lower lambda.
It's much lower. It's estimated around 0.667, maybe think 20/3 coherence remaining.
And therefore, a much higher ACL.
Exactly. That low lambda-c produces a strong AC of about 0.333 or 13. And this amplitude correlates nicely with the strong coupling constant, alphas, which determines the strength of the strong force.
And its properties.
Because it's so highly decohered, its field intensity is incredibly condensed, leading to that huge amplitude. This directly explains why it's so powerful, but also has such an incredibly localized influence. It basically never extends beyond the scale of a proton or neutron. It confines quarks. You pull quarks apart, the force gets stronger, snapping them back. That's the ultimate expression of highly concentrated, low coherence energy.
Wow. Okay, so looking at all three, the pattern is really clear. The unified interpretation is high lambda-c means low ACL in long range, like electromagnetism. Low lambda-c means high ACO in short range, like the strong force.
You nailed it. That's the core insight. It's like a spectrum. Lambda is the informational purity, ATID is the energetic punch. And they trade off. It reminds me a bit of entropy and energy less order can lead to more intense local energy release. The paper also suggests ACA is fundamentally tied to how sharply the phase of the coherence field changes. Big changes, big amplitude.
So how does UCTE formalize this? Is there a core equation that pulls lambda AC and the emergence of these force groups U1, SU2, SU3 together? The unified coherence equation.
Yes, there's a framework for it. Conceptually, lambda is seen as defining these quantized layers of symmetry. As you reduce coherence from the perfect vacuum state where lambda 1, you cross thresholds, and these different force fields, represented by the gauge groups $, emerge.
So lambda C sets the layer, ACA is the resulting strength, and the $9 are like the labels for those layers.
That's a good way to put it. Lambda is the degree of alignment, ACA is the field strength projection, and $9, like U1, SU2, SE3, are the specific symmetry structures that stabilize at those different coherence levels.
And the simplest mathematical relationship they propose is that linear model.
Yes, the most straightforward model is remarkably simple. AC equals 1 lambda C. where lambda day is that coherence coefficient measuring the remaining coherence.
And you're saying this incredibly simple equation actually works for the forces we just discussed.
Astonishingly well.
Good.
Let's plug in the numbers we used. For U1 EM, lambda AC prox 19155, so AC equals 0.915 equals 1.155 matches. For SE2 weak, lambda AC approx 1.875 Y, so AC equals 1.875 approx 0.1254 matches. For SU3 strong, lambda AC approx 0.667 leather, so ACEC approx 0.3333 matches.
That is amazing. The simplest possible linear relationship perfectly recovers the amplitudes that align with the known force constants. That level of internal consistency from such a simple premise is, well, it's elegant. Almost too elegant.
It is striking, and this simplicity is often a sign you're onto something fundamental in physics. Now, to help visualize this whole process, the paper uses an analogy that coherence cascade and gauge group emergence, which they sometimes call a scroll diagram.
A scroll diagram, like rolling out a map of forces based on coherence.
Exactly. Imagine a vertical spectrum. At the very top, you have lambda AC, $1 though, that's the hypercoherence zone, the pure omnilectic vacuum. Perfect symmetry, no forces projected yet, just potential.
The source code, basically.
Sort of, yeah. Then, as you move down the scroll, as lambda AC decreases, you cross thresholds.
And forces appear.
Yes, the cascade just below lambda C, one has to say, when lambda C is roughly above 0.9, specifically Crescent 0.9154, the U1 electromagnetic field emerges. First ripple, AC approx 0.0851, least decohered force, keep going down. Around lambda AC of 0.8751, threshold maybe 0.8 lambda AC, 0.9, the SU2 weak force appears, more symmetry breaking. AC approx 0.1254. Further down still, around lambda AC sim 0.6671, threshold maybe 0.6 lambda AC 0.11, the SU3 strong force crystallizes. Significant decoherence, strong AC approx 0.3333.
And does the scroll keep going? Does it predict things beyond the forces we know?
It does. The model naturally extends. It projects an SU5 grand unified force potentially emerging around lambda AC approx 0.51, threshold 1 non-day rate like 0.62. Here, ace field would be about 0.5. This is where theorists think the electromagnetic weak and strong forces might unify at incredibly high energies. Even deeper, maybe an air hyperunified field symmetry around lambda AC approx 0.251. Threshold lambda AC of 0.244, giving a very strong AC approx 0.755. This hints at an even more fundamental layer. And finally, at the very bottom, lambda AC equals 0.00 low. This represents total decoherence. Complete fragmentation, maximum amplitude AC equals $1.
So this scroll isn't just descriptive, it's predictive. It visually maps out how these fundamental structures, the gauge groups, just pop out at specific coherence levels. It makes symmetry breaking feel less abstract, more like phase transitions.
It really does. And while this linear model, AC equals 1 lambda, is powerful and matches the core forces, the paper does mention that reality might involve more complex nonlinear relationships too, like exponential decay or fractal patterns, especially for describing things like quark confinement or maybe the very early universe. So the framework has flexibility built in.
Fascinating. So the forces are handled. What about the other big players? Mass, charge, spin.
Yeah.
Okay, this next part about mass. This feels like it really shakes things up. We're so used to thinking of mass as just something the particle has.
Yeah.
An intrinsic property.
Right, like its fingerprint.
Yeah. But UCTE says,
No. Not quite. It's one of the most radical departures. UCTE proposes that mass is not an intrinsic property. It's not fundamental in that sense.
so what is it then?
It's defined as the inertial residue of symmetry reduction, or, maybe more intuitively, the appearance of coherence loss across a resonance interface.
Okay, say that again. Coherence loss.
It means that as a system becomes less coherent, as its lambda AC value goes down, deviating more from that perfect vacuum state, mass increases. Mass emerges as a direct consequence of coherence being lost or reduced.
So particles don't have mass. They're the mass resulting from their specific level of coherence loss.
You've got it. That's the paradigm shift. Mass is an emergent property determined by the coherence dynamics.
Which leads to a mass coherence equation similar to the amplitude one.
Exactly, and it's beautifully simple. 1/8 molar dollar, lambda AC dollar.
Okay, 1 of Eller's mass. What's dollar?
Number dollar represents some maximum mass scale, the potential mass you could get from complete decoherence, theoretically. So that's the scale.
And the 1 of Eller lambda apart. That looks familiar.
It should. It's the exact same term we saw in the linear amplitude equation, AC equal 1 over lambda.
So,
Wow.
wait, does that mean mass is directly proportional to coherence amplitude?
$1 propto AC, precisely. That's a huge connection UCTE makes. Mass is coherence amplitude, scaled by none dollars. More amplitude, more energetic projection means more mass. It's a natural consequence of the resonance condensation in this framework. The standard model needs the Higgs mechanism to give particles mass, but UCTE suggests mass arises directly from the coherent structure itself.
Wow, okay, if mass depends on coherence loss, $1 lambda, how does that explain the huge differences in particle masses? The mass hierarchy. Photon massless, electron tiny, top quark enormous.
This is where UCTE really offers a neat explanation. The different families of particles are seen simply as existing at different quantized levels of coherence, different lambda-c states. The mass hierarchy is just a reflection of the coherence-amplitude cascade.
So walk us through it.
Okay, photons and neutrinos. They're almost perfectly coherent. Their lambda mass is basically 1.0. So $1 lambda c is almost zero. Result, near zero mass. To the least disturbed ripples. Electron, muon, tau. These leptons show increasing coherence loss. The electron is a small disturbance, lambda slightly below 1. The muon is a bigger disturbance, lower lambda c. The tau even bigger, even lower lambda c. As lambda c drops, $1 lambda c increases, and so does their mass. Electron light, muon 200x heavier, tau 17,000x heavier. These ratios UCTE suggests reflect quantized steps down the coherence ladder. Top quark, what are the heaviest particles we know? And UCTE, it represents a state of very significant decoherence, a much lower lambda c resulting in a very large mass. Higgs boson. Even the Higgs fits in. UCTE interprets it not as the giver of mass necessarily, but as a scalar particle representing a specific coherence condensation state, maybe around lambda c approx 0.55, a sort of halfway point which explains its substantial mass. So the whole zoo of particle masses becomes ordered, explained by this single parameter, lambda c.
That's the proposal. Mass hierarchy equals coherence amplitude cascade. Different families are just different rungs on the ladder.
And you mentioned mass can also be seen as curvature, like bending spacetime.
Yes, there's a more advanced formulation using tensor math. Mumali lambda-c. That looks complicated, but the idea is simple.
Please simplify.
Imagine the coherence field is like a stretched rubber sheet. Perfectly flat is the vacuum, lambda c nano 1, no mass. If you disturb it, create decoherence. It's like pushing down on the sheet. It bends, it creates curvature, tension.
Okay.
Mass in UCTE is that tension or curvature. It concentrates where the coherence field changes sharply where decoherence is happening.
So mass equals coherence tension.
Exactly. And particles, they're like stable, resonant coherence vortices, little whirlpools or knots in that sheet. The vacuum is where the sheet is smooth and flat. It fundamentally redefines mass not as stuff, but as a geometric expression of coherence loss. The theory even suggests mass should be quantized in specific bands or levels.
Mind blown.
Yeah.
Okay, let's shift to charge, another fundamental property. How does UCTE handle that? Is it also emergent?
Yes, and in a really elegant way. UCTE proposes charge isn't just some arbitrary electrical property, it's a topological winding number.
Winding number, like how many times something wraps around something else.
Exactly. It's about the geometry of the coherence fields phase. Imagine the coherence has a phase, like an angle. The equation is Franck-Jack-Dedalero. Basically, you go in a loop around a point, and you count how much the coherence phase changes or wins, divide by 2, a full circle, and you get the charge.
Can we visualize that? You mentioned a color wheel analogy.
Yeah, think of the coherence phase as being represented by colors on a wheel, spread out across space. A charged particle is like a tiny vortex or defect in this color field. Now, if, as you go around the core of this vortex, the colors cycle through the entire wheel exactly once red back to red, say that's a full 360-degree or 2 winding. UCTE says that corresponds to an integer charge, like 2q all to 1 or -1 for the opposite winding, like an electron or proton.
The complete wrap. Makes sense. What about fractional charges, like the quarks inside protons and neutrons, plus 23 9 to 13? That's always seemed weird.
UCTE has a beautiful explanation, fractional winding. If the phase only wraps, say, 1/3 of the way around the color wheel, 120 degrees, or 2-3 radians, as you loop the vortex core.
You get a charge of 13.
Exactly. Fractional charges are just incomplete vortex wraps. The paper suggests these might be projections of higher dimensional windings, stable only when confined together within a larger system, like quapes inside a proton, where the total winding adds up to an integer.
That is incredibly intuitive. So charge isn't just a label. It's literally the shape, the topology of the coherence field around a particle.
Yeah.
And quantization, why charge comes in chunks, just falls out naturally from the geometry. Like you can only have whole or specific fractional wraps.
Precisely. Quantization comes from the harmonic boundary conditions of these windings, not from some arbitrarily assigned value. It's a geometric constant. UCTE frames charge within a larger structure called the coherence harmonic algebra, where different winding patterns give rise to neutral, integer, or fractional charges.
Okay, this is huge. Mass from coherence loss, charge from coherence winding. What about spin? Does that fit too? This leads to the Coherence-Spin-Charge CSC tensor framework, right? The unified map?
Yes, the CSC framework aims to tie it all together. It defines any particle state using a unique CSC state vector.
SC particles ID card?
What are N, S, and Q again?
N is the mass coherence eigenlevel. It's directly related to mass higher. N means lower coherence and thus higher mass. It tells you the particle's rung on the coherence mass ladder. Lambda is the spin quantization, standard spin. 0 for scalars, like Higgs. 12 for fermions, electrons, quarks. 1 for vector bosons, photons, gluons, etc. Is the spin quantization. Standard spin, EuroQ, is the charge winding number we just talked about, how the coherence phase wraps around it. So every particle has a unique NSQ address, and you can visualize this.
Yes, as a 3D CSC lattice. Imagine a 3D coordinate system.
Okay.
The x-axis is the coherence index n, representing mass level. The y-axis is spin says, and the z-axis is charge q. Every known particle, and potentially unknown ones, occupies a specific point in this lattice.
A cosmic periodic table, almost, but based on coherence geometry.
That's a great analogy. It unifies mass, spin, and charge as geometric coordinates derived from coherence, not as separate, unrelated properties. Each point isn't just a particle, it's a coherent resonance tensor.
And interactions. How do particles combine or decay in this lattice view?
Simple vector addition rules can describe basic interactions. If particle A, high NA SA QA combines with particle B, when A, MB, SB, QBA, the resulting particle C might be roughly at NA1A plus MD, SA plus SB, QA plus QB, obeying conservation laws.
Let's take the proton example again. 2 up quarks, 1 down quark.
Right. An up quark might be 1 in 12 plus 23 $, and a down quarked 1 in 12 known of $13. Combine 2 ups and a down. Charges add. Plus 23 plus 23 13 equals plus 1. Charge conservation is topological winding conservation. Charges add. Spins add up vectorially to give the proton spin 12. Charges add. Mass is related to n add up 2, though binding energy complicates the simple sum. The proton's n reflects the combined coherence curvature.
So the structure provides a geometric explanation for particle composition and conservation law.
Exactly. It maps out the fundamental resonance structures allowed by the coherence field, covering both known particles and potentially predicting new ones.
Okay, so this CSC Alice, this 3D lattice, isn't just about organizing what we already know. You're saying it's actually predictive. It points towards physics beyond the standard model BSM.
That's one of its most exciting aspects. Yes, it integrates all the familiar standard model particles, putting the electron here, the photon there, quarks, gluons, W bosons, all positioned according to their mass level n, spin s, and charge q. But because the framework is built on these fundamental coherence principles, it naturally suggests where other currently hypothetical particles might fit in.
So it's not just recategorizing, it's actively generating hypotheses for new discoveries. That's a big deal. What kind of BSM candidates does UCTE predict based on this CSC framework?
It points towards several interesting possibilities, falling into roughly 3 main categories. 1, supersymmetric SU-SY partners. SU-SY is a popular BSM theory that proposes every known particle has a superpartner with a different spin. Like the electron, fermion spin 12, having a partner called the selectron, scalar, spin 0.
Right. SU-SY predicts a whole shadow zoo of particles. How does UCTE handle them?
UCTE provides a natural geometric location for them in the CSC atlas. They would appear as sort of parallel ghost layers in the lattice. If the electron is at a certain n, S12, Q1, its selectron partner would be at roughly the same n, Q1, but with S0. They'd be vertically offset in the spin dimension, indicating a direct resonance link.
So CCY partners are like coherence echoes in a different spin layer.
That's a great way to put it. It gives CCY a potential geometric underpinning within the coherence framework. You'd expect selectrons, neutrinos, spin 0 partner of neutrino, quarks, spin 0 partner of quark, and so on, populating these parallel layers.
Okay, that's one category. What else?
2, multi-winding baryons and mesons. Remember how charge is topological winding?
Yeah, fractional charges are incomplete wraps. Integer charges are full wraps.
Well, UCTE suggests you could potentially have stable states with multiple windings. We already know of particles like the delta++, delta++ baryon, which has charge +2. UCTE sees this naturally as a double winding state.
Could there be more, like charge +3?
The theory suggests yes. hypothetical triple winding particle, delta plus plus plus, or other exotic combinations. In the CSC lattice, these multi-winding states would sit vertically stacked along the charge Q axis above their single winding counterparts. They'd represent highly compressed coherence states, possibly forming in extreme environments like neutron star cores or high-energy collisions. It expands the possibilities for charge states.
Interesting. A richer charge landscape.
Yeah.
And the third category, you mentioned it relates to a huge mystery.
3. Coherence-derived dark matter candidates.
Yeah.
Yes, dark matter. The standard model has absolutely no candidate particle for it. UCTE offers a natural possibility.
Oh.
It suggests that dark matter could consist of particles that are electrically neutral, charge quire dollars, but have undergone very deep coherence reduction, meaning they have a very high mass level N, making them heavy.
So heavy neutral particles born from extreme coherence loss.
Exactly. In the CSC atlas, these would cluster in the high mass, high N, zero charge region. Think of particles like a coherence-neutral scalar, spin 0, or a heavy neutral fermion, spin 12. They'd be fundamentally part of the coherence spectrum, but because they're neutral and very massive, low coherence, they'd interact very weakly with normal matter, mainly through gravity or perhaps extremely subtle coherence effects. This could explain why dark matter is so elusive.
So UCTE doesn't just accommodate dark matter, it sort of predicts candidates based on its core principles.
It provides a framework where such particles arise naturally from the coherence cascade, rather than needing to be bolted on as an extra ingredient.
This really highlights the power of visualization with the CSC atlas, that 3D lattice, the maps. It seems crucial for grasping these connections and seeing where new physics might hide.
Absolutely. It turns abstract quantum numbers into geometric coordinates. Mass, spin, charge become dimensions in a space defined by coherence. It lets you see the relationships, the potential symmetries, the harmonic structures. It provides an intuitive yet rigorous map to guide theoretical exploration and hopefully future experimental searches for these BSM particles. It makes the whole particle zoo feel less random and more like parts of an underlying coherent structure.
All right, we've covered a lot of ground, the core ideas, how it explains forces, mass, charge, spin, even predicting new particles.
Yeah.
But now for the crucial reality check, the scientific standing. How well does UCTE actually connect with experiments? What's the evidence, and what are the roadblocks?
That's the million-dollar question, isn't it? On the plus side, UCTE scores points for experimental alignment with those numerical matches we talked about.
Right, the coherence amplitudes, ACT for the forces, matching up with the fine structure constant, Fermi constant, strong coupling constant.
Exactly. Getting those fundamental constants to fall out naturally from a simple model, AC equals 1 lambda c, is non-trivial. It's a significant piece of quantitative evidence suggesting the framework might be on the right track. When theory predicts numbers that match reality so closely, you have to pay attention.
That is definitely compelling. But you also mentioned current limitations. What's the main hurdle for proving or disproving UCTE right now?
The biggest challenge is that the core parameter, the coherence coefficient lambda c itself, isn't something we can currently measure directly with existing experiments. We don't have a coherometer sitting in our labs.
So we can't just point a device at a particle and read off its lambda cc.
Not yet, no. That makes direct, comprehensive verification difficult right now. However, the paper doesn't just leave it there. It proposes indirect ways to test the theory.
Like what?
For example, looking for subtle effects of coherence damping in precision quantum measurements, or searching for tiny specific shifts in neutrino oscillations that might be influenced by underlying coherence dynamics. Or perhaps designing experiments that probe atomic lattices tuned to specific coherence resonance thresholds. The theory isn't untestable in principle, it just might require new experimental techniques or looking at existing data in a new light.
So the challenge is devising experiments sensitive to this deeper layer.
Precisely. Building the bridge between the theoretical concept of lambda-c and measurable lab observables.
Given these strengths and challenges, how does the author, Lillian, actually rate the theory himself? What's his assessment of its logical coherence, explanatory power, and its meta-ontological grounding? That last one sounds deep.
He provides a pretty detailed self-assessment in the paper. 1, logical coherence. He rates this as high. He argues the internal logic is rigorous, consistent, and deeply interconnected. It integrates concepts like gradients, symmetries, fields, scalars, tensors without obvious contradictions. It hangs together very well mathematically.
So it's internally consistent. Good start. What about explanatory power?
Rated very high. And I think we've seen why. It offers elegant answers to those big why questions. Why do forces have different strengths? Why do specific gauge groups emerge? Why does losing coherence create structure? Why the inverse relationship between lambdas and ACI? It tackles mysteries the standard model leaves open, often without needing extra baggage, like extra dimensions or tons of ad hoc particles.
Okay, and the meta-ontological grounding. What does that mean, and how does it rate?
That's about its fundamental basis, its story about what reality is. He rates this as unmatched. His point is that standard physics often treats forces and particles as somewhat abstract concepts. UCTE, however, posits a clear first principle, the coherence gradient as the single origin for all structure. Matter, fields, maybe even spacetime itself emerge from this one thing.
A unified origin story.
Exactly. It defines forces as mere coherence residues, making them less abstract, more geometric. This kind of deep, unified foundation is something many feel physics needs to move forward.
So based on all that, he gives odds of correctness. That's bold.
It is. He estimates above 75% that this framework contains the correct underlying form or geometry of universal emergence.
Wow, 75%. That's high confidence.
Extremely high. But he qualifies it. He estimates only a 30–40% chance that current experiments can measure or confirm in its full form. The tools might not be there yet, but he stresses, it can be simulated, modeled, and approximated with increasing detail.
So the conclusion is?
His conclusion is that the theory is coherently radical, not incoherently speculative, meaning it's revolutionary, but built on solid logic and numerical hints, making it a serious contender for a post-standard model paradigm. The next steps, he suggests, are refining the math and figuring out those experimental connections.
The clear path forward. And this brings us to the potential implications beyond physics. If coherence is this fundamental, could it apply elsewhere?
Absolutely. The paper touches on this, suggesting vast interdisciplinary potential. In biology, could UCTE model things like DNA resonance? Maybe DNA stability comes from it being a highly coherent structure. Or perhaps neural patterns in the brain, even consciousness itself, could be understood as complex coherence dynamics. Biological systems as coherence engines. In technology, this understanding could lead to entirely new tech. Imagine coherence computing, manipulating coherent states directly, or new energy devices based on resonance coupling or optimized decoherence. Maybe even new materials designed around coherence principles.
Coherence computing. That sounds like something out of science fiction.
It does, but if the underlying principle is correct, the technological possibilities could be immense. The paper even outlines ideas for a biocoherence Lagrangian, suggesting ways to apply these ideas mathematically to life itself.
The scope is just staggering, from subatomic particles to biology and tech. Hashtag outro. Well, we have certainly taken a deep dive today. We've explored the unified coherence theory of everything, UCTE. We've seen its core proposal, that coherence, or rather its reduction, is the fundamental stuff of reality.
Yeah, we saw how it suggests force strengths, particle masses, even charge and spin aren't just arbitrary features, but emerge naturally from changes in this underlying coherence.
Explaining things like the force hierarchy, why the strong force is strong in short range, electromagnetism weak and long-ranged, through that inverse relationship between coherence and amplitude, ACM.
And redefining mass as a residue of coherence loss and charge as a topological winding number in the coherence field. Really fundamental shifts in perspective.
We also looked at the Coherence-Spin-Charge atlas, that 3D map, not just organizing known particles, but actually predicting new ones, ECSY partners, multi-winding states, even potential dark matter candidates, all fitting within this single coherence framework.
It really aims to provide that unified picture, that deep ontological grounding, suggesting a single first principle, the coherence gradient from which all the complexity we see emerges. It paints a picture of a universe deeply interconnected through these coherence dynamics.
It really does. So here's a final thought for you, our listener, to maybe ponder. Consider this universe UCTE paints, where every particle, every force, maybe even the structure of space-time, perhaps even your own thoughts, are just different patterns, different vibrations in a vast field of coherence. If that's true, if we could truly understand this fundamental resonance, maybe even learn to manipulate it, what could that unlock? What kind of new technologies, what deeper insights into consciousness, what new forms of energy might become possible?
It really opens up incredible possibilities.
The quest for a theory of everything is far from over, but perhaps this idea of coherence, this deep dive we've taken today, shows us a genuinely new and promising path forward. It might just be the guiding light we've been searching for.